Good afternoon, everyone. I welcome you again in this session on digital image classification. I am Dr. Poonam S. Tiwari, and today we will be discussing digital image classification. So, to start with, first of all, we should understand what is digital image classification. Multispectral classification or digital classification is the process of sorting out pixels into a finite number of individual classes or categories of data based on their data file values. If a pixel satisfies a certain set of criteria, the pixel is assigned to the class that corresponds to that criteria. Multispectral classification may be performed using a variety of algorithms. We can have hard classification using supervised or unsupervised approaches. In case of natural features where the boundaries of the features are not very clear, we can go for classification using fuzzy logic. In the features which have certain difficulties in identification, we can use hybrid approaches which often involves the use of ancillary information. So, as we have already said, what is digital image classification? It is grouping of similar pixels and also separation of dissimilar ones. Also, it is assigning the class label to the pixels, and this all we do to result in a manageable size of classes. What we have understood is that if we have a 8-band data set and it is a 8-bit data set, and we are having 4 band in our data set, so we can have numerous combinations of pixel values of all these bands that can be there for any particular pixel. So for these numerous or we can say infinite values, we sorting out these values so that we result in a finite number of classes, and these classes will be then discussed with the image interpreter and then particularly assign the class labels to these classes. The classification method or the image interpretation method, or what we can say how to extract the features from the image, these can be either manual, they can be computer assisted, or they can be stratified also. The manual methods you have already been told about uses visual image interpretation techniques. It uses all the elements of visual image interpretation: tone, texture, shape, size, all these 9 elements which were discussed in visual image interpretation are used in manual classification method. So manual classification can be done on a hard copy image, or you can open the image on the software, and on that soft copy image also you can identify the features and mark the boundary of the features manually and digitize it manually. The computer assisted classification is multispectral or digital image classification, which we will be discussing today. In multispectral classification, instead of using all the parameters of the image, all the elements of the image, we are using only the tone that is represented by digital number of the pixel. So only based on the pixel values we are trying to sort out the pixels into the classes, and then for these classes we have to identify what is the particular information class to which these pixels would belong. That means we would assign the class labels to these classes. So today's discussion is based only on the computer assisted method of classification, that is digital image classification. Within digital image classification also we are all only going to discuss the hard classification methods, in which we either classify a pixel into a particular class or we do not classify the pixel into that particular class. That means we, for the questions that we have asked, we will have a simple yes and no answer. That means if the pixel belongs to a class or it does not belongs to a class. So that is why these classification methods or algorithms are called as hard classification methods, and there are various methods of hard classification, supervised and unsupervised. In both the approaches we have various algorithms. In today's lecture we will be discussing all these algorithms. So why should we go for digital image classification or multispectral classification? So as we have already discussed, to translate the continuous variability of image data into map patterns that provide meaning to the user. Also to obtain insight in the data with respect to ground cover and surface characteristics, to find anomalous patterns in the image data set. It is cost efficient in analysis of large data sets, as we have tried to understand that if we are going to make a land use land cover map of entire Uttarakhand state. So if you are using the manual methods of feature extraction, then it might take a lot of time for processing it. Whereas if you are using digital methods, then the process becomes effective and cost effective and time effective also. Also, if we are using the computer methods, the results can be reproduced. When you are making a map manually, that means you are tracing it out, and if you want to make another map of the same type, you will have to again trace it out. Whereas if you are using digital image processing methods, then once you have stored the results of your classification, the same results can be reproduced, and you can have as many copy as you want. It is more objective than visual image interpretation. Visual image interpretation is dependent on the analyst who is performing the interpretation. If the analyst is very good, he is able to interpret it very nicely, then you will have a very good classification. Otherwise, it might have errors. Whereas digital image classification, because it is based on set of rules, and these rules are based only upon the digital numbers, that is why it is more objective in nature. In visual image interpretation, we can display only 3 bands at a time, but in case so all the information of 3 bands only is taken into account when we are performing visual image interpretation and doing the information extraction from that method. Whereas if we are using multispectral classification or digital classification, the effective analysis of complex multi-band interrelationships can be taken into account. So before proceeding into the lecture, I would like to explain a few terms which we will be using in the lecture. The first term is dimensionality of the data. So spectral dimensionality of the data is determined by number of set of values being used in a process. So in case of multispectral data set, because every band is one set of data values, so every band is one dimension. So as many number of bands you have, the data is that many dimensions. So if you have a 10 band data, then your data is called to be a 10 dimensional data. If you have n bands in your data, we will call it as n dimensional data. In image processing, each band of data is a set of values. An image with 4 bands of data is said to be a 4-dimensional image. Then the next term that we will be using is measurement vector. The measurement vector of a pixel is the set of data file values of one pixel in all the n bands. So suppose we have these 3 bands and we have this v pixel. So this is the first pixel, v pixel. So in the first band, the value of this pixel is v1. The value of the same pixel in the second band is v2, of the same pixel in third band is v3. Then the measurement vector would be equal to a matrix v1, v2, v3. Similarly, we can have for certain applications, we are not considering one single pixel, we are considering more than one pixel. In such cases, we would be required to find out mean, standard deviation, variance and other statistical properties for these set of pixels. So likewise, we can calculate or we can make mean vector, standard deviation vector and so on. So suppose in this case we are having 7 pixels. So mean of these 7 pixels in band 1 is mu1. Mean of these 7 pixels in band 2 is mu2. Of the same 7 pixels in band 3 is mu3. So mean vector mu would be equal to mu1, mu2, mu3. So when the measurement vectors of several pixels are analyzed, a mean vector is often calculated. This is the vector of the means of data file values in each band. It has n elements. Similarly, we can calculate standard deviation vector, variance vector and so on for a set of pixels. Now coming to image space, we are used to looking at the image in where the pixels are arranged in form of rows and columns. So you can see these pixels are arranged in form of rows and columns. An image is an array of elements corresponding to reflected or emitted energy from instantaneous field of view. Or what we can say is it is a spatial arrangement of the measurement of reflected or emitted energy. So the manner in which we are used to looking at the image, this is called as image space. But when we are doing the multispectral classification, we will transform this image into the feature space so that we are able to do the classification properly. So feature space is simply a graph of data file values of one band of data against the values of another band. So if we are using a two band data, this is a two band data, it will have a two dimensional curve, two axis curve. So there are three pixels, pixel A, pixel B, pixel C. The value of pixel A in both the bands is 34 and 25, of pixel B is 34 and 24, pixel C is 11 and 77. When we plot these values so that band 1 is on one axis, band 2 is on x axis, pixel A, pixel B, pixel C are represented as single dots, then this is called as a feature space. So here I have shown you only three pixels, but you can have all the pixels of the images can be plotted like this, and such a plot would be called as a scatter plot. Now why we are transforming the image space into feature space? Because if you can see, pixel A and pixel B, they are having similar values in both the bands, 3425 and 3424. Therefore, pixel A and pixel B are falling at similar location. They are close by each other in this graph, in this feature space, whereas pixel C, which is having completely different brightness value, it is plotted at a different location. So we can make boundaries of these around these pixels and group these similar pixels and separate out the dissimilar pixels, which was our problem of digital image classification. That I have shown you in a feature space in only 2 dimension. You can have multi-dimensional feature space. Graphically, I can show you only 3-dimensional feature space, but mathematically you can have n-dimensional feature space in which all the n axes would be at 90 degree to each other. So in that n-dimensional feature space, these pixels would be plotted. That would be called as an n-dimensional scatter plot, and in that n-dimensional scatter plot, the feature boundaries would be marked and the image classification would be carried out. The other term is spectral distance, because how we find out whether these pixels are similar to each other or not would be done based on the spectral distance. So Euclidean spectral distance is distance in n-dimensional spectral space. It is a number that allows two measurement vectors to be compared for similarity. The spectral distance between two pixels can be calculated as d is equal to square root of summation from I is equal to 1 to n di minus ei whole square, where capital D is the spectral distance, small as n is the number of bands which we are using in the classification, I is a particular band, and D and E are two different pixels. So pixel value, or what we can say is pixel value between the difference in pixel value between two pixels in a band, square of it, and go on summing throughout all the bands. That means if you have n bands, you go on doing it for n times. For every band you have one difference, sum it up, square and sum it up, square and sum it up, and then finally take a square root of it. So that would be called as spectral distance. It is simple Euclidean distance that we have done in our class 8th or class 9th. Now coming to image classification process, the first thing that we have to do is selection of the image data. The training data sets have to be generated. The training and selection of algorithm is to be done. Running of the actual classification is to be carried out. Then the classification data would look something like this. We have to compare it with either the original remote sensing data or from the ground and do the validation, do the accuracy assessment. So coming to types of digital image classification, basically we have two types of digital image classification. First one is supervised classification and other is unsupervised classification. As the name itself suggests, supervised classification. That means we are supervising the computer to perform the classification. Whereas in unsupervised classification, the computer is not supervised, it does the classification on its own. So let us see what is supervised classification. In supervised classification, the identity and location of some of the land cover types such as urban, agriculture, wetland are known a priori through a combination of fieldwork and experience. The analyst attempts to locate specific sites in the remotely sensed data that represent homogeneous examples of these known land cover types known as training sites. Multivariate statistical parameters are calculated for these training sites. Every pixel, both inside and outside the training site, is evaluated and assigned to the class of which it has the highest likelihood of being a member. Likewise, we should also try to understand what is unsupervised classification. In unsupervised classification, the identities of land cover types to be specified as classes within a scene are generally not known a priori because the ground reference information is lacking or surface features within the scene are not well defined. The computer is required to group pixels with similar spectral characteristics into unique clusters according to some statistically determined criteria. The analyst then combines and relabels the spectral clusters into information classes. In supervised training, it is important to have a set of desired classes in mind and then create the appropriate signatures for the data. Supervised classification is usually appropriate when you want to identify relatively few classes, when you have selected training sites that can be verified with ground truth data, or when you can identify distinct homogeneous regions that represent each class. On the other hand, if you want the classes to be determined by spectral distinctions that are inherent in the data so that you can define the classes later on, then the classification is better suited for unsupervised classification. Unsupervised training enables you to define many classes easily and identify classes that are not in contiguous, easily recognized regions. So based on your requirements, you can select which type of classification you want to perform. Now one by one we will discuss supervised and unsupervised classification in detail. To start with supervised classification, In supervised training, you rely on your own pattern recognition skills and a priori knowledge of the data to help the system determine the statistical criteria, which we call as signatures for the classification purpose. To select reliable samples, you should know some information, either spatial or spectral, about the pixels that you want to classify. So these samples, for which we know that these pixels are true representative of the class, these pixels are called as training samples. Training samples are set of pixels that represent what is recognized as a discernible pattern or potential class. The system calculates statistics from the sample pixels to create a parametric signature for the class. To select the training sample, the training samples for a particular class should be collected from homogeneous environment. If the training data is being collected from n bands, then more than 10 n pixels of training data is to be collected for each class. There are a number of ways to collect the training site data. You can either use a vector layer, you can define a polygon in the image, or you can use a class from a thematic raster layer from an image file of the same area. That means the results of unsupervised classification can also be used as training samples. Once we have collected the signatures, it is very important to evaluate these signatures, whether the signatures are good enough for classification or not. So a very basic method of evaluating the signatures is by drawing ellipses. So we can view ellipse diagrams. The ellipses are drawn based on the mean and standard deviation of the training samples in the different bands. So these ellipses are drawn, and the two signatures would be called as separable if these signature ellipses are separated either in any one of the band pairs. So as you can see here, the signature is overlapping, both these signatures are overlapping. So we will have confusion in these part of the pixels which are falling in this part, whereas these two signatures are distinct because these two signatures do not have overlap between them. The other method of finding out whether the signatures are separable or not is the signature separability. Signature separability is a statistical measure of distance between two signatures. The separability can be calculated for any combination of bands that is used in the classification, enabling you to rule out any bands that are not useful in the result of the classification. You can use any of the distances such as Euclidean distance, divergence, transform divergence, Jeffreys-Matsushita distance, Bhattacharya distance, and so on, for evaluating whether the signatures are separable or not. The information about these distances you can find in any literature about digital image processing. Once we have finalized our signatures, the next step is to select the appropriate classification algorithm. There are various supervised algorithms which may be used to assign an unknown pixel to one of the classes. The choice of a particular classifier depends on the nature of input data and the output that is required. The parametric classification algorithms assume that the observed measurement vector, which we call as XC, obtained for each class in each spectral band during the training phase are Gaussian in nature. Non-parametric classification algorithms make no such assumptions. There are many classification algorithms, that is parallelepiped, minimum distance to means algorithms, maximum likelihood algorithm, and so on. Coming to parallelepiped classification algorithm. In the parallelepiped decision rule, the data file values of candidate pixel are compared to upper and lower limit. These limits can either be the minimum and maximum data file values of each band in the signature, or the mean of each band plus and minus a number of standard deviations, or any limit that you specify based on your knowledge of the data and the signatures. There are high and low limits for every signature in every band. When a pixel's data file value are between the limits for every band in a signature, then the pixel is assigned to that particular signatures class. Therefore, if the low and high decision boundaries are defined as LCK, that means low boundary of the band of the class C in band K, is equal to mu CK, that means mean of class C in band K minus standard deviation of class C in band K. This would be the low boundary, and the high boundary would be mean plus standard deviation. So this we will do for all the bands. So for all the bands we will have the boundary limits. So the parallelepiped algorithm becomes that BVIJK, that means brightness value of any individual pixel in a particular band should fall between the lower and upper boundary of the class in that particular band. As you can see here in the picture, we have taken 5 different classes: class 1, 2, 3, 4 and 5. For class 1 we have created the boundaries, class 2 we have created the boundaries, class 3 the boundaries, 4 and 5. There are 2 individual pixels, pixel A and pixel B. Pixel A, as you can see, is falling within the parallelepiped or box for class 4. That is why pixel 4 would be classified as class A. The pixel B is not falling in any of these classes. So if we are using parallelepiped algorithm, then the pixel B would be left as unclassified pixel. Now what should happen if we have overlap in these parallelepipeds? In cases where a pixel may fall into the overlap region of 2 or more parallelepipeds, you must define how the pixel must be classified. The pixel can be classified by the order of the signatures. The pixel can be classified by the defined parametric decision rule, or the pixel can be left as unclassified also. The advantages of this classification algorithm is that it is very fast and simple. It gives a broad classification, thus narrows down the number of possible classes to which each pixel can be assigned before more time-consuming calculations can be made. It is not dependent on the normal distribution of the data. The disadvantage is that since the parallelepiped has corners, pixels that are actually quite far spectrally from the mean of signature may also be classified. So you can see here parallelepiped corners compared to the signature ellipse. So in these areas, in this triangular area, this portion is quite far spectrally from this from the mean, whereas even if the pixel is falling here, it would be classified as this particular class. The next algorithm of supervised classification is minimum distance to means classification algorithm. This decision rule is computationally simple and commonly used. It requires mean vectors of each class in each band from the training data. Euclidean distance is calculated for all the pixels with the signature mean. So we are calculating distance, Euclidean distance of that pixel with the mean of the signature, where mu ck and mu cl represent the mean vectors for class C measured in band K and L. Any unknown pixel will definitely be assigned to one or of any classes. There will be no unclassified pixel. The advantage is that since every pixel is spectrally close to either one sample mean or other, so there are no unclassified pixels. It is fastest after parallelepiped decision rule. The disadvantage is that because any one of the distance would be minimum, so pixels which should not be classified also becomes classified. Also, another disadvantage is that it does not consider class variability into account. So, for the same example, if we see for these 5 class means, then here A and if we are classifying it using minimum distance to means classification algorithm, now the distance between A and the mean of class 4 is minimum, so A would definitely be assigned to class 4. But for B, when we calculate distance with all the class means, we see that the distance between B and the class mean of 3 class 3 is minimum, so B would be assigned to class 3. To overcome the problems of minimum distance to means classification algorithm, Mahalanobis decision rule was designed. Mahalanobis decision is similar to minimum distance except that the covariance matrix is used in the equation. The variance and covariance are figured in so that clusters that are highly varied lead to similarly varied classes. The formula for calculating distance for Mahalanobis decision rule is D is equal to x minus mc transpose of that inverse of covariance minus x minus mc. X is the measurement vector of the pixel, mc is the mean vector of the signature of class C. The advantage is that it takes the variability of classes into account. Unlike minimum distance or parallelepiped, it may be more useful than minimum distance in cases where statistical criteria must be taken into account. The disadvantage is that it tends to overclassify the signatures with relatively larger values in covariance matrix. As you must have observed, we are using the covariance matrix as such in the formula. It is slower to compute than parallelepiped or minimum distance algorithm. Mahalanobis decision rule is parametric, meaning that it relies heavily on the normal distribution of the data in each of the input band. The next classification algorithm and a very used classification algorithm is maximum likelihood or Bayes decision rule. The maximum likelihood decision rule is based on the probability that a pixel belongs to a particular class. The basic equation assumes that these probabilities are equal for all classes and that the input bands have normal distributions. If you have a priori knowledge that the probabilities are not equal for all classes, you can specify weight factors for particular classes. This variation of the maximum likelihood decision rule is called as Bayes decision rule. The equation for maximum likelihood or Bayes classifier is as follows. D is equal to natural log of AC, where AC is the percentage probability that any candidate pixel is a member of class C, minus 0.5 natural log of covariance matrix minus 0.5 x minus mc transpose covariance matrix inverse multiplied by x minus mc, where x is the measurement vector of the candidate pixel, mc is the mean vector of the sample of class C, and covariance matrix is the covariance matrix of that particular somewhere we are using determinant of covariance matrix for a particular class. The advantage of maximum likelihood classifier is that it is the most accurate of the classifier if the input samples or clusters have a normal distribution, because it takes into account the most of the variables it takes into consideration. It takes the variability of classes into account by using the covariance matrix, as does Mahalanobis distance. The disadvantage is that an extensive equation that takes a long time to compute. The computing time increases as we increase the number of input bands. Maximum likelihood classifier is parametric in nature, means it relies heavily on normal distribution of data in each input band. It tends to overclassify signatures with relatively large values in the covariance matrix. This finishes supervised classification. Now we will start a detailed discussion about unsupervised classification. Unsupervised classification requires only a minimum amount of initial input from the analyst. The numerical operations are performed that search for natural groupings of the spectral properties of pixels. User allows computer to select the class means and covariance matrices to be used in the classification. Once the data are classified, the analyst attempts to a posteriori to assign the natural or spectral clusters to the information classes of interest. Some clusters may be meaningless because they represent mixed classes. Clustering algorithm used for unsupervised classification generally vary according to the efficiency with which the clustering takes place. Two commonly used methods are chain method and ISODATA clustering. Starting with the chain method. Chain method operates in a two-pass mode. That means it passes through the registered multispectral dataset 2 times. In the first pass, the program reads through the dataset and sequentially builds clusters. A mean vector is associated with each cluster. In the second pass, a minimum distance to means classification algorithm is applied to whole dataset on a pixel by pixel basis, where each pixel is assigned to one of the mean vectors created in pass 1. The first pass automatically creates the cluster signatures to be used by supervised classifier. So in the first pass, the analyst is required to supply the 4 types of information, which is capital R, the radial distance in spectral space used to determine when a new cluster should be formed. C, that is a spectral space distance parameter used when merging clusters when capital N is reached. Capital N is the number of pixels to be evaluated between each major merging of the cluster has to take place, and C maximum would be the maximum number of clusters to be identified. So let us take a hypothetical example and try to figure out what is chain method. In this hypothetical example, we have 3 pixels. It is a 2-band data and we have 3 pixels, pixel 1, pixel 2 and pixel 3. Pixel 1 has a value of 10 and 10, pixel 2 has a value of 20 and 20, and pixel 3 has a value of 30 and 20. So we have plotted these 3 pixels and we have these in form of a scatter plot. Now when we start the chain method, so in our case we have taken capital R is equal to 15 units and capital C is equal to 20 units. So capital R is the radial distance which we will see, by which we will evaluate whether 2 pixels will join and form a class or it will make a new class of its own. So to start with, it will go to pixel number 1. Since it doesn't have any other cluster, so pixel 1 will be made as a new cluster. Now cluster 1 has only one pixel, which is pixel 1. So the mean of the cluster 1 would now be 10 and 10. So now it will go and evaluate pixel 2. For evaluating of pixel 2 means whether pixel 2 has to be merged in cluster 1 or it will make a new cluster of its own. So for finding out that, we will calculate the spectral distance between pixel 2 and mean of the cluster 1. So this distance, spectral distance D comes out to be 14.14. This is less than the R distance. So pixel 2 will be merged in cluster 1. So once our cluster has these 2 pixels, the mean of the cluster gets shifted and it is now at 1515 location. Now pixel 3 would be evaluated. The distance, spectral distance between pixel 3 and mean of cluster 1 would be checked. This distance comes out to be 15.81, which is more than the capital R distance specified by us. So pixel 3 would make another cluster of its own. So like this, new pixels go on merging in these clusters and the mean of the clusters go on shifting. So this complete thing is pass 1. So by the end of pass 1, we have mean of all the clusters, mean of the Cmax clusters that are required by us. And in pass 2, the pixels are assigned to one of the Cmax clusters using minimum distance to means classification logic, as we have already discussed in the supervised classification. The final cluster mean data vectors are used in a minimum distance to means classification algorithm to classify all the pixels in the image into one of the Cmax clusters. The next unsupervised algorithm is ISODATA clustering. ISODATA stands for Iterative Self-Organizing Data Analysis Technique. So ISODATA represents a comprehensive set of rule of thumb procedures that have been incorporated into an iterative classification algorithm. The ISODATA algorithm is a modification of k-means clustering algorithm, which includes the merging of clusters if their separation distance in multispectral feature space is below a user-specified threshold, and rules for splitting a single cluster into 2 clusters. ISODATA is iterative in nature because it makes a large number of passes through the remote sensing dataset until specified results are obtained instead of just 2 passes. ISODATA does not allocate its initial mean vectors based on the analysis of pixels, rather an arbitrary assignment of all the Cmax clusters take place along an n-dimensional vector that runs between very specific points in the feature space. These are the parameters that are required for ISODATA algorithm. These parameters are C maximum, which is the maximum number of clusters to be identified, capital T, which is the maximum percentage of pixels whose data file values are allowed to be unchanged between the iterations. Capital M is maximum number of times ISODATA is to classify the pixels and recalculate cluster mean vectors. We have also to specify the minimum members in a cluster, the maximum standard deviation for a cluster, split separation value. This is split separation value if theoretically it is taken as 0.0. If the split separation value is changed from 0.0, then it takes the place of standard deviation, maximum standard deviation, and it would be used for splitting of the cluster. And minimum distance between cluster means. So capital M is maximum number of times the ISODATA is to classify the pixel. So these many times the ISODATA would be carried out. Minimum members in a cluster. So suppose we specify 10 members in a cluster. So any cluster which is having less than 10 pixels would be merged into the nearest cluster. Then maximum standard deviation for a cluster or split separation value, both will work for the same. If the cluster has a standard deviation more than this value, then the cluster would be splitted into 2 parts. Then minimum distance between cluster means, if there are 2 cluster means which are closer than this minimum distance, then these 2 clusters would be merged together. And to stop the ISODATA algorithm, either the capital M should reach, that means maximum number of times ISODATA is to classify pixels, either this has been achieved, or maximum percentage of pixels whose class values are allowed to be unchanged between iterations, this has achieved. So this is a graphical representation how ISODATA is performed. In ISODATA, the initial distribution of 5 hypothetical mean vectors using one standard deviation in both bands as beginning and ending point. So this is mean, this is one standard deviation, positive, negative. Similarly in band 2 also, so we take up this area and divide it arbitrarily into 5 parts, because 5 is the maximum number of clusters that are required. Now we have 5 means, 1, 2, 3, 4 and 5. Now all the pixels both inside and outside the cluster would be now checked with the mean of the cluster based on the minimum distance to means classification algorithm. Then the redistribution of pixels would take place. Based on these redistribution of pixels, the means would be shifted. Now again it will be checked. Now again we have new means, again it will be checked. This process will go on until the capital T threshold is reached, or capital M number of times ISODATA has classified the pixels. In between the both the iterations, the splitting and merging of clusters is also carried out. So you can see distribution of in the first initial phase how the 20 clusters have been distributed, and finally how the 20 clusters have been distributed. Now once we have carried out classification, it is very important that we assess how good we have performed the classification. So for that purpose we carry out accuracy assessment. Accuracy assessment is a general term for comparing the classification to geographical data that are assumed to be true in order to determine the accuracy of classification process. Usually the assumed true data are derived from the ground truth data. So based on this data, we create an error matrix. So once the classification has been sampled, a contingency table, or what we also call it as error matrix or confusion matrix, this is developed. This is a table which is used to properly analyze the validity of each class as well as the entire classification as a whole. In this way, we can evaluate in more detail the efficiency of the classification. So let us discuss how we create this confusion matrix and how we calculate the accuracy of the classification using the confusion matrix. So one way of to assess the accuracy is to go out in the field and observe the actual land class at a sample of locations and compare to the land classification it was assigned on the thematic map. So what we can do is we can select some sample points on the classified image, go to the ground and check what is the class in the classified image and what is the class on the ground, or what is the actual class. So now after once we have this table, then we will put that table in form of a matrix. Now this matrix is a square matrix which will have same number of columns as the number of rows, and these number of rows and number of columns will be the same as number of classes that you have in your classification. So suppose in this classification we have 3 classes, class A, class B, class C. We have 3 classes in the ground truth also, A, B and C. Now a total number of 136 pixels were selected. These many samples were selected at which the ground truthing was carried out. So out of these 136 pixels, 50 were found to be in class A. These are ground truth classes. You can see the ground truth classes are in the columns. Okay. So A column has 50 pixels. That means 50 class pixels or 50 points were identified as class A, 40 points were identified as class B, and 46 points were identified as class C. Now, out of when we have checked these reference points with our thematic data, out of these 50 points which we have found that these points were falling in class A, 35 points were classified as A in our thematic map. You can see AA, we have a number of 35. 10 points were wrongly classified in class B and 5 points were wrongly classified in class C. Like this, we have to take the table and fill the entire matrix. So once this matrix is generated, then we can make the further calculations. The first calculation that we can make is what is the overall accuracy of the classification. So overall accuracy means how good you have performed the classification. So if you look at this table, is at this matrix, you can see the diagonal elements represent the correctly classified pixels. This is 35, 37, 41 because diagonal is AA, BB and CC. Okay, so diagonal elements represent the correctly classified pixels. So how many have been correctly classified divided by how many were classified. So in our case, the overall accuracy would be 35 plus 37 plus 41 divided by total number of pixels that we are using, total number of samples used for accuracy, that is 136. So 83% of overall accuracy of classification we have achieved. So, but just because 83% classification were accurate overall, it does not mean that each category was successfully classified at that particular rate. So, we can calculate the individual accuracy of the individual classes also. So, individual class accuracy we can have from two point of view. One is from user's point of view and the other is from producer's point of view. The user's point of view means the user of the data, user of the classified data. The user of the classified data would want to know that in the thematic map that was supplied to him, and if there are 50 pixels or 39 pixels which were classified as class A, how many of them were correctly classified? Because he doesn't have any ground truth information, he doesn't know what is there on the ground. So, he only has to use the thematic map. So, how many are the correctly classified pixels from the total number of pixels that are classified? So, that means 35 divided by 39 would give me the user's accuracy of class A. Okay. Similarly, we can have user's accuracy of class B and user's accuracy of class C. 90% 39 pixels were classified as class A, out of which only 35 were class A. That means 2 plus 2, that means 4 pixels were wrongly committed into it. We are wrongly committing that these 4 pixels are class A, whereas they are not the class A, or what we can say, they are false positive. So, when we find out the error here, so 10% would be the error of commission. The error of commission, we have wrongly committed that these pixels are belonging to this particular class. So, 10% would be from user's accuracy, you can find out error of commission also. The next accuracy is the producer's accuracy. Contrasted to user's accuracy is the producer accuracy, which has a slightly different interpretation. The producer's accuracy is a measure of how much of the land in each category was classified correctly. The producer of the map wants to know that from the ground how correct I have done the classification. So, out of 50 pixels which should be there for class A, only 35 have been classified as class A. So, 35 divided by 50, that means 70% would be the producer's accuracy for class A. So that means 30% of pixels have been omitted. 30% of pixels have been omitted. So 30% would be the error of omission, or what we can say is false negative. So from this assessment, we have 3 measures of accuracy which addresses subtly different issues. Overall accuracy, which takes no account of error, source of error, either error of commission or error of omission. Users accuracy, which measures the proportion of each thematic map class which is correct, and it accounts the error of commission also. The producer accuracy measures the proportion of land base which is correctly classified. It includes the error of omission also. There is another parameter by which we can show the accuracy of the classification, that is by kappa coefficient. Another measure of map accuracy is the kappa coefficient, which is a measure of proportional improvement by the classifier over a purely random assignment of classes. For an error matrix with r rows and hence the same number of classes, same number of columns, let A is the sum of r diagonal elements, which is the numerator in computation of overall accuracy. Let B is sum of r products row total multiplied by column total. So kappa hat or kappa coefficient would be equal to NA minus B upon N square minus B, whereas N is the total number of pixels, that is 136. A is the sum of correctly classified pixel, 35 plus 37 plus 41. B is 39 multiplied by 50 plus 50 multiplied by 40 plus 47 multiplied by 46. That is row total multiplied by column total. So kappa coefficient or kappa statistics, kappa is also tested statistically. So these are the methods by which we can assess the accuracy of the digital classification. So this is what is there in digital image classification. Thank you so much for your attention, and this is my email address pwoonam@iirs.gov.in. We will take a small break. Please prepare your questions. We will be joining in for an interactive session in a few moments. Thank you.